And so far we have in the program, we have been talking about different quantum algorithms for solving partial differential equations. We looked at extensively into nonlinear PDEs. And today's session, we're going to talk about something a little bit different. We're going to see how quantum algorithms are being used to inspire better and better classical algorithms. And for that, we have with us today Dr. Hessam Babaee from the University of Pittsburgh. Hessam is an associate professor in the Department of Mechanical Engineering and Material Science, and he earned his PhD in mechanical engineering and a master's in applied mathematics, both from Louisiana State University in 2013. And his research focuses on developing low-rank approximation techniques for high-dimensional dynamical systems. And his work has been funded by very many organizations, including NASA, NSF, NIH, and the Air Force Office for Scientific Research. And we're very excited that he's here with us today to share his latest work on adaptive tensor interpolation. And over to you, Hessam. Looking forward to your talk.
Thank you so much for the kind introduction. So so let me get started. I want to talk about the role of interpolation for doing low-rank approximation with tensor networks, and show you why interpolation we think is extremely important to make these algorithms generalizable to different PDEs. So I would like to just acknowledge my current and former students who contributed to this talk, and also my collaborators, especially Dr. Peyman Gibi and as well as Dr. Jackie Chen at Sandia, where we collaborated with Dr. Jackie Chen on extending this algorithm to turbulent combustion. So reducer modeling has a deep history in fluid mechanics, and I grew up in fluid mechanics community. In fact, proper orthogonal decomposition, POD, reduced order modeling is first proposed in fluid mechanics. In fact, this book was published in '95, the first edition of it, which is you go and extract a subspace from, you first have to simulate or collect experimental data for fluid dynamics observations, and then you perform an SVD on the snapshot matrix, and then you can extract a subspace from that data. That subspace is static, spanned by a set of orthonormal modes, and then you project that your governing equation to that subspace. So now that works for low Reynolds number flow. Low Reynolds number flows are flows that have less, the ratio of the convective force to the viscous force is smaller, so it's less convective. But if you increase the Reynolds number, so that means if your flow is relatively more convective, then you get this kind of a structure. So this is actually a simulation from my PhD thesis, jetting cross flows at the jet. You see a lot more structures coming in here, and this is a NASA bump simulation by Ali Uzan and Mujib Malik. So you see an extremely complex flow field develop. So the computational cost of doing these simulations is enormous. So, and we know this kind of POD reduced order modeling doesn't work, doesn't have predictive capability here. So this has been established in fluid dynamics community, and it's very well understood why that's not the case, why you cannot do that. So this was the first motivation for me to explore this quantum inspired algorithm. I have been working in this area for the past more than 10 years now. So this is not quantum computing, this is just quantum algorithms. So I want to emphasize that it's just algorithms that are using quantum to solve quantum many-body problems. So what is interesting about these algorithms is that you can, first of all, you don't have any offline costs, so you don't need to generate any data. So you can essentially just directly solve the PDE. And all of these formulations give rise to time-dependent subspaces. So as opposed to POD, where you actually extract the basis as static, here the bases are time-dependent. And just because of the workflow that they're time-dependent, and you don't need any priori data generation to extract the subspace. In fact, you don't have the issue of extrapolation, essentially, to unseen conditions which exist in a POD setting. So I think this community knows the history very well here. So just quickly, this is based on Dirac Frankel variational principle, and then density matrix normalization group, actually showing that you can actually approximate high dimensional functions. This is from the applied math side of things. I look at these algorithms. There's this nice review paper in year 2000, looking at all the literature up to that point. I think it was this seminal paper in 2007 by Koch and Lubick, where they showed you can use this kind of algorithm to solve generic matrix differential equation, not just the ones that are specialized to quantum many problems, but essentially any generic matrix differential equation. They introduced the notion of Riemannian manifolds, and that geometric perspective. I think it's a very nice way of looking at this. And then the extension of that to tensor train or matrix product state. Now, obviously, tensor network is a much bigger field. Essentially, it has many applications, as I'm sure you all know. Other motivations for me are high dimensional PDEs. You have Boltzmann transport equations. These are extremely important PDEs, physics. So 6-dimensional PDEs also work in turbulent combustion. We solve Fokker-Planck type equation for closure modeling of turbulent combustion. I don't want to go through this, the details of this, but just this dimension of this PDE can easily get to up to 100, because you essentially track a probability density function for a species, joint probability density function for a species, and you can easily have an order of 100 species. And also parametric PDEs, where you have a deterministic PDE, but then you have a whole bunch of parameters that are changing. And so this dimension psi can be of order of very large number, easily up to 10,000. So these are the problems that dimension is high, but there is also problems dimension is 3, like turbulent combustion problem. But when you discretize this, because of the multi-scale nature of the problem, you end up with a gigantic dynamical system, easily order of billions, and this is direct numerical simulation of turbulent flow. So we are limited actually how large of a Reynolds number we can do. So if we can do any saving here and we can extend there and do direct numerical simulation of high Reynolds number, that's highly desirable. And because there's no modeling here, essentially. But if you don't want to do that, you have to do turbulence modeling, which introduces all kinds of errors. So this is just the gist of what we have done so far. Like in one slide, if I want to give you an overview of the entire methodology, what we have done so far. So we take a dynamical system, this Rn, and then you have to choose how you metricize or tensorize this, which is an important choice. But this is a representation of this dynamical system. So essentially have a d-dimensional tensor, or if this is 2, it is a matrix differential equation. And so far we have been able to develop these algorithms for a matrix low-rank approximation, tensor train, and Tucker tensor. Most of my talk I explain matrix because that is just easier, but then I'll talk about the extension of that to tensor train as well as Tucker tensor. I'll talk a little bit about the Tucker tensor. So what this ends up, this interpolation, is that if you have your existing PDEs with existing discretization, and that's represented in this tensor differential equation, what this algorithm allows you to do, essentially the low-rank approximation of these amounts to interpolate in solving the existing PDE, the existing discretization at certain points. Essentially interpolate the solution onto these points, and you can approximate the rest of these points by using the tensor interpolation in everywhere else. So these points, and I'll explain the details of the algorithms in the next few slides. These points, which points it picks, it depends what kind of tensor low-rank approximation we pick, which one of these architectures, and for each one we have an interpolation algorithm. And so these points, the data from these points are collected into a generic algorithm, the cross algorithm, which is the interpolation algorithm. Then it reconstructs essentially the solution everywhere in the compressed form, and then it updates the sampling points, and it'll sample a different set of points. So in that sense, it actually makes the application of these two complex codes much easier. And I'll go through the details of that. So let me just cover a little bit about the dynamical low-rank approximation, because we had been using that for several years before developing this interpolation algorithm. Let me just pull this. So dynamic. So again, let me talk about matrix differential equation. Imagine you have this matrix, and most of my examples are fluid dynamics examples. And imagine these are different samples of the fluid dynamical system. So you have n by s, and you're seeking to approximate this in this low-rank form. The dynamical low-rank approximation gives this very nice geometric representation of solving these equations in the low-rank form, where every point is in this space. Every point is a matrix of size n by s. Every point on the manifold is a matrix of rank R. And here, when I say rank R, it's not in the physics context. Rank here, what I mean by rank is the rank in the mathematical sense, rank of a matrix. So rank of a matrix is not 2. Rank of a matrix is the number of non-zero singular values of that matrix. So then the right-hand side of dynamical system, this f hat, and so anything I show with v hat is a rank R. Anything with not hat, it's a full rank. So the right-hand side actually sticks out of this plane. If you have nonlinearity here or summation of some terms, the right-hand side is a vector. So every vector is also a matrix of the same size. The dynamical low-rank approximation essentially is a Galerkin projection of this dynamical system to this tangent space. So essentially, you need to project this to the tangent space, and that way you can evolve this always in the low-rank form. Essentially, it's solving this minimization problem using Riemannian optimization, and the optimality conditions of this minimization problem allows you to derive the direct evolution equation for each of these components. So that way you can actually just solve these equations, these 3 equations, as opposed to the full lower model equations. So this is what is so nice about this is divorced from any assumption in terms of Hamiltonian or structures that are a lot of it hard-coded in quantum mechanics. But this is a generic way of solving. So this any matrix differential equation. Yeah, I mean you have to have some regularity on the f, but other than that, it's pretty generic. And this, of course, has been extended to tensor train or hierarchical Tucker tensor decomposition. This formulation, obviously more involved, but the same. The essence of it is the same. There are several issues in solving these equations that has received a lot of attention. There's an inversion of the singular values in the right-hand side, which causes ill conditioning because you always want to push this to smaller and smaller singular values. That's how we get more and more accurate solutions. But the smaller singular values means singularity. We have to do something for it. I would say that problem is fully resolved by these fantastic papers. There's a series of papers here, but I think this 2021 paper actually completely resolves this issue, and you can actually integrate this system with even 0 singular values. It's a different form of this based on projector splitting. But I would say still time integration is challenging, like especially if you want to do high order time integration, and definitely implicit time integration. If you look at a lot of scientific computing problems that usually have stiffness, so explicit time integration is really not appropriate or not cost effective. So this is also quite challenging to solve these systems implicitly. The other thing which was the focus of my work is that if this f is a complex function, especially it has nonlinearity, especially non-polynomial nonlinearity, the rank of this matrix it can be full if you have non-polynomial nonlinearity, even though the inside matrix is a rank R matrix. If you apply, for example, e to the power of component-wise of that matrix, you get a matrix that is full rank. And then you don't want to store a full rank matrix because we assume these matrices are very large. And so then you lose the computational efficiency using this kind of algorithm. So you have to do something about the role of nonlinearity. The other thing was that if you have existing code, implementing this algorithm can be a bit challenging because you have to implement new set of equations, and you have to do it carefully to get the efficiency out of it. So the fact that the intrusiveness of this algorithm is also, it adds to the human cost, not the computational cost. So just a summary of developments, and I'll cover these 3 papers that we have done. So essentially, what we have done, developed a methodology based on interpolation that I'll go through in the next few slides that allows you to solve essentially any kind of nonlinearity. So you don't lose efficiency by having non-polynomial nonlinearity, and we have extended this to a standard time integration schemes, explicit and implicit Runge-Kutta, and also multi-step schemes. For implicit, we have implicit Runge-Kutta and also backward differentiation formula. We've extended this to metrics, like I said, Tucker tensor and tensor train, but we are extending this to much more involved, much more complex tensor trees. We've extended to applications. So acidic quantification was really the primary application, but also flow stability for arbitrary time-dependent base flows and turbulent combustion. I'll talk a little bit about the turbulent combustion application. We have done also direct numerical simulation of turbulent flows, high-dimensional PDEs, and also skeletal kinetics. So a lot of applications are in focus on a lot of it on fluid dynamics type applications. So let me just give you the gist of the algorithm, which is actually it's relatively easy to understand. So we assume this is the matrix differential equation where V is a matrix of size n by s. So this is what we call full normal nonlinear matrix differential equation. Assume you discretize this, let's say, explicit Euler for the sake of simplicity. So like I said, anything with hat, that means rank R. So I assume the previous time instant is already of rank R. And so if I start from initial condition that rank R and calculate the solution next time step, this solution, because of this addition and the nature of this F, this is in general either a higher rank or full rank matrix if this has non-polynomial nonlinearity. Okay, so this is just the discretization of full normal. So what we do here, so you need to bring this back to a rank R somehow, right? So the way we do this, obviously you can take SVD of this, but SVD of this defies the whole purpose, because if you want to take SVD of this, you need to know all the entries of this F, and if you and exactly computing all the entries of this F is what we want to avoid. Otherwise, we don't get any computational efficiency. That would be even more costly than solving the original equation. So what we do is based on CUR approximation. So CUR is also a low rank approximation. So C stands for column, R stands for rows, and U is a middle matrix. And here this is shown schematically here. Imagine this V of K is exactly this solution. In order to construct a rank R approximation of this, so this is also in Tensor, it's called cross approximation. But it was first introduced in this 97 paper and it's known as pseudoskeleton in that paper. So what you do, you just select R rows if you want to construct rank R rows, R columns and R rows of this matrix. And then the COR allows you to construct a low rank approximation by just these three matrices, these are the actual these are a subset of the columns of the matrix, the selected columns, selected rows, and this middle matrix is the intersection of the columns and rows inverted. So what's the advantage? Okay, so what's the advantage of this is that it allows you to construct a rank R approximation by only sampling R columns and R rows. So which is actually the minimal number of entries of a matrix you need if you want to build a rank R approximation. So R columns are rows, so you get actually efficiency because we are not computing the right-hand side solution at any of these areas, gray areas, essentially. And you can actually estimate, once you have this approximation, you can estimate the solution everywhere else. So this is matrix interpolation because this rank R matrix is exactly equal to the target matrix at these selected columns and rows. So there is no error at the column and rows, selected columns and rows, but there is obviously low rank approximation error in between. But the question is that which columns and rows you pick, because that absolutely is critical. So you can select columns and rows and you get a very, very bad low rank approximation. It's a rank R approximation, but it could have very large error. So we compare the error against SVD, which we know is the optimal low rank approximation. So the idea is that which columns and rows you pick to have lower error. And so here we use this DEIM algorithm, or discrete empirical interpolation method algorithm, which was introduced in 2010 and then 2016 was extended. So this algorithm allows you to pick a near optimal set of columns or rows. So this original algorithm was just developed for vector reduce or modeling. So if you have a low rank basis, then you can actually come up with a good set of optimization. Let me just quickly, because I intentionally, let me just show these two slides that explains the interpolation algorithm. Let me explain the basic concepts in terms of interpolation. So imagine, so this is to just show you the importance of interpolation. So imagine you have a vector f, and you want to project that to a subspace U, and U is a set of orthonormal modes. So this has R columns. I want to approximate the best A here. So the best A, and so I want to approximate F, construct an F hat. So U is known. I want to know what is the best coefficient A. So the best coefficient A is just do an orthogonal projection of that vector to the space spanned by the columns of this U, which is U transpose F. So this is U transpose F because this, I'm assuming here, this is orthonormal. You can make it non-orthonormal, that's fine. But geometrically what we show, you can see here, if you have this vector, if I want to compute the best approximation of its orthogonal projection. So this gives us the best approximation. But in terms of computation, this requires access to all entries of F. So in order to compute this best A, I need to know all entries of this F. And when we do computation, this F is the right-hand side of the matrix of tensor differential equation. We don't want to actually evaluate all of it, because if you do, you lose computational efficiency. So interpolation offers an interesting alternative here. So you can approximate this A by just pinning down your approximation to the target vector at R points. And so if you do that, then essentially you can say this is, so then you have zero error at these interpolation points and you have errors in between. And I'm using MATLAB notation here, where P is the index of the selected entries of this F. And then the A, you can compute A through interpolation by just inverting this submatrix, which is an R by R matrix, and the value of F at these points. Okay, so here the advantage is that we only needed access to these R entries of F rather than the whole thing. But then the key is that what points do I pick? Because any set of R points I pick, I get a different A. And so the question is that which one is the best set of points? If you look at this geometrically, this is an oblique projection. So if this was the orthogonal projection, you can see here, this is the optimal projection. And by doing this, you're essentially giving an angle to this. And ideally, you want to be as close as possible to the orthogonal projection. So DEIM algorithm, which I was just talking about, discrete empirical interpolation method, is a method that allows you to find this set of points, a near optimal set of points, by just having access to the basis U. So we know we have basis U, and the DEIM algorithm, essentially all it needs is just a subspace U. And what it does, so if I just cover this error bound quickly, so in this interpolation, the difference, the error between the target function and the approximation is bounded by, so this I minus U transpose F is the optimal error. This is the orthogonal projection error. This is the length of this dotted line. And then you get an amplification factor because we are doing interpolation. So this number is always larger than 1. And it's this number is the norm of this submatrix that we invert. So essentially, you want to pick points such that the norm of this submatrix is as small as possible. So if you want to do that, you can do it in a full search, which is combinatorially difficult because you have to pick R points out of you have to check all the combination of R points out of N points, which is difficult and computationally expensive. DEIM essentially is a greedy algorithm that finds you a near optimal set of points by minimizing this condition number of this matrix successively in a greedy fashion. And you can actually use QDEIM. This is another paper that came out after that. Essentially, it's 2 lines of MATLAB code to extract these points. So this is based on pivoted QR. But what is so nice is that you can see the error bound here. So you know just you're off from the optimal error by just this A to P. And that's exactly what we use. Let me just go back to the CUR. So now let me give you the overview of the algorithm. So we have the solution in the low rank form from the previous time instant, and we apply the DEIM algorithm to the left singular vectors. of that, and that way we get rows. And then we apply DEIM to the right singular vectors and you get columns. And we only solve that full order mall at these selected columns and rows and nowhere else. And then the rest of it is just processing this data. The COR algorithm, the way I showed it in the previous slide, that's numerically unstable. So there is a QR version of that, which is analytically the same, but numerically stable. So what you do, you first sample the columns, and then you perform a QR on the columns. So you construct an orthonormal basis for the column of the matrix. Then by solving the form at these rows, then you can interpolate any other column to the span of those columns. So essentially, these three simple lines allows you to construct a low-rank solution of this matrix, and this algorithm is stable. And you can improve the condition number of this algorithm by sampling more rows than columns. So that way, instead of this inversion, you will have a pseudo-inverse. So this oversampling, you can actually oversample, and like I said, you can improve the condition number of that A to P. But this algorithm, the QR, is exactly analytically identical to this. But like I said, it doesn't have this inversion of this matrix, which can become unstable if you have near zero singular values. So just geometrically showing this is that if you think about, you could have taken SVD of this solution and come back to the manifold. This essentially allows you to just come back to the manifold in an oblique way. And so we demonstrated this algorithm for solving random PDEs in this paper. And then after that, we extended this to, so here we only did explicit time integration, high order explicit time integration, and then we extended that to implicit after that. So what you can also show is that the error you get from this kind of approximation for matrix is a multiplicative factor larger than the error of SVD. And this error is bounded by the A to P, which is the A to P and A to S are the condition number of the matrices that you invert for the columns and rows. So you can show actually if A to P and A to S are small, which exactly that's what DEIM achieves, so you can get something that is very close to SVD. And then we also make the whole methodology rank adaptive, and we extended this to Tensor, where we look at the last singular value divided by the Frobenius norm of the low rank matrix that we extracted. And if this number is larger than some number, we add a mode. And if it's smaller than some number, we remove a mode. So let me talk about the extension of this to Tensor Train. Let me just, so Tensor Train, you essentially do the same thing, but you have to do this carefully core by core. So here, this is a demonstration of a 5-dimensional tensor where we first peel off the first tensor. So we call this CUR DEIM algorithm. You first peel off the first core. And if you're familiar with the cross tensor approximation in the paper by Oseledets, essentially the algorithm follows the same strategy as in that paper, except that here we do all of these things with DEIM, discrete empirical interpolation method, rather than with the max-vol type sampling methods. So you extract the first core and you compute that. You don't compute this because this is still a high-dimensional tensor. I mean, here this demonstration is 5-dimensional, but we want to apply this to very high-dimensional tensors. And then you reshape this. Essentially, this, if you want to go back and look at it, is in tensor train SVD. Essentially, anytime you take SVD, that essentially is replaced with the CUR, but you don't compute the right singular vectors because that's a high-dimensional vector, and you don't want to form this. So you do everything only the blue cores are calculated at any step of the algorithm, and not the yellow one. And you do that successively by just peeling off core by core, and then you can construct your low-rank approximation. So the details of that is in this paper. And we will give, assuming we have the same rank R. So R rank here is the bond dimension in quantum physics, is the indices here, assuming we have the same rank here. You exactly sample the number of points you sample. So this is all done by interpolation. The number of samples we do is R squared D by n times n. So here, this is an n to the power of d tensor. So d is the dimension of the tensor, and n is number of points in along each mode. So it's actually kind of nominal. So if I have different bond dimension, obviously it would be those bond dimensions that you sample. And this reconstructed tensor is exactly equal to the target tensor at those interpolated points. And then it'll have error in between. The same way as we had for COR. So let me just show you a little bit results here. So we apply this to, this is a stochastic PDE. So you have advection, diffusion equation, and reaction. So this time is reaction, and assuming psi1 and psi2 are random numbers. And so the velocity field is solved by solving Navier-Stokes equation. So what you see here, these interpolation points evolve with time. So we took two different approximation here. One with so the full normal has 4.7 times 10 to the 9 degrees of freedom. And this is just by calculating this matrix. We have order of 19,000 grid points in both x1 and x2 direction, and we sample this with 500 points along psi1 direction, 500 Monte Carlo samples along psi2 direction. So this is the size of this. And then we also did it for a smaller number of samples so that we can actually calculate the error and do all of this to show that the methodology is accurate. So with this one, we get order of 171 compression factor. Obviously, as you increase the number of samples, your rank doesn't necessarily increase. So you get this order of 11,000 compression ratio. And then here this problem is shown in this figure by SADR. And so here we look at the scaling. We increase the number of points in these two directions. And we show the scaling here, show that the scaling is linear. And then we also show the full normal. So anything here, the form is full normal. The TT-COR DEIM, this is 4-dimensional. So this is the second problem. Let me also explain this second problem. So this is a 4-dimensional advection reaction equation where we are solving this PDE on a 4-dimensional grid. And you see here we have this kind of non-polynomial nonlinearity where existing methods would have failed here for this kind of problem, because even if V is low rank, e to the minus V is full rank. So here we compare the even relative memory of the 4D case, this case, versus the reduced form, which is this one, and this for the stochastic advection reaction problem. Probably a simpler setup to just show that we can solve very large problems. So this is a synthetic PD. It's not PD. It's a tensor differential equations where you have a 100-dimensional tensor, a time-dependent tensor, and you have this 1 over this kind of form, which is not necessarily, you don't see a large gap between singular values for this type of function. So here we have 100 dimensions. Each dimension is discretized to with 70 grid points, which makes the total size of the problem 70 to the power of 100. And this analytical tensor actually satisfies this tensor differential equation, which is a pointwise tensor. So there's no differential operator here. It's just pointwise. But we intentionally made B equal to a non-integer 0.9, which means that this is a non-polynomial nonlinearity here. And so even if V is of rank R in tensor train, the V to the power of 0.9 is going to be full rank. So here we show that with different epsilon, so we do this rank adaptivity for core by core basis. When I explained the matrix, it was just essentially one core, but here we do it core by core, so each core can have its own rank. And so we have different threshold for different ranks. And so we could calculate the error here as a subset of points, because we cannot form this full tensor. So we calculate the approximation here. We have the analytical solution, and then we calculate the error. And this is with different rank adaptivity criterion. And you can see the rank profile here. So this is the rank of the first core, the rank of the 50th core for different thresholds. So you see rank as time evolves, rank also changes with time. But this actually, we solved this problem my student solved this problem in his laptop with very limited memory, and you can show actually the total number of points that you have is order of less than 1 million for doing this simulation. So let me explain and wrap up with this last example, which is application of the matrix tensor differential equation to turbulent combustion. So this is in collaboration with Sandia National Lab. So all of the implementation is done by Ki-sung, who was at the time postdoc at Sandia in S3D, which is co-developing Dr. Jackie Chen's group, and also we collaborated with Christian on this project. So all of these simulations results that I show are produced and developed, implemented by Ki-sung. So let me give you a little bit background about turbulent combustion. So turbulent combustion, you have to solve Navier-Stokes equation, compressible Navier-Stokes equation, and I have to solve this species transport equation. So essentially, you have to solve a PDE for each of these species. So if you have chemical reactions, the chemical reactions result in a number of species, and so essentially we track the mass fraction of each of those species. And this PDE, rho is density, phi I is this mass fraction of that species, u is the velocity field, which is determined by solving the Navier-Stokes equation. And this is a diffusion term, and this is a chemical source term. So all of these species are nonlinearly related to each other. So I don't want to go through the cost of this, but this is enormously computationally costly problem for turbulent problem. I mean, turbulent flow itself is very costly. And then essentially when you do turbulent combustion, on top of that, all the challenges you had for turbulent flow, now you have to worry about combustion and reaction. And reaction brings its own limitation in terms of the number of grid points to capture really thin flame structures. And then it'll introduce stiffness to the problem because this chemical source term has time scales that could be much, much smaller than the convective and diffusive time scales of the flow. So it adds to an already expensive and costly computational problem, already adds a much more difficulty. And we focus only on this equation and not on the rest of the turbulent flow. So we solve Navier-Stokes equation, but we look at this species transport equation. But what is so nice about this equation is that you can matricize this equation by just putting these species next to each other. And even at very high Reynolds number, this matrix actually has low-rank structures. And the reason is that all of these vertical structures, so this is a laminar flow example. This is really not turbulent flow. But actually it demonstrates the low, you can visually kind of see the low-rank structures here because all of these structures are the same, but you just have different mass fraction on this. So you can actually compress this quite a bit. So essentially we recast this vector differential equation, which is number of grid points by number of species times 1, to a number of grid points by number of species. And then we solve this low rank, this matrix differential equation, this is just recasting this equation in the low rank form. So we first introduce this methodology. Here we use dynamical low rank approximation, where we couldn't get any computational savings here, but we could show that you can solve this equation and sustain the low rank approximation error and still get an accurate result. This chemical source term is extremely complex. It's got all kinds of nonlinearities. It's linked to thermodynamic table, so it's quite involved actually. So we tested this algorithm for a number of test cases in turbulent flowing, from one-dimensional reaction to two-dimensional to three-dimensional turbulent flames. So 6 cases overall. So here, this is a summary of all the. So here we also introduced a innovation in terms of time integration, where we actually exploit this low-rank approximation to alleviate the stiffness issue, and that contributes to the efficiency that we get here. And you can see the speed of, so we solve the full normal under with the existing codes, and we also solve it using this reduced normaling. We call this on-the-fly reduced normaling because there is no prior information needed. I see the speed up we got order of 10. I mean, this one is less because it really depends also on the stiffness of the problem. But in this problem, we got order of 100 speed up, and this has 1.5 billion degrees of freedom. This is the size of the three-dimensional grid, but on top of that, you solve for all the species. And the number of species are mentioned. So this is 19 species, 53, 53, 90, 41, and so on and so forth. So let me show you a little bit of these results. So this is one of the two cases. Anywhere you see DNS, that's a full Ormol. Anywhere you see TDBCR is the reduced Ormoli. And so here I'm showing the animation. I'll show animation of the two of the species mass fraction. This is mass fraction of H2O, and this is H, and this is O, and this is, so these are four different species shown here. So now this is the full Ormol, and this is the reduced Ormol. And you see here, these are the rows of the matrix we sample at. So here we also do oversampling, so you see more points than the rank here. But you can see just visually that this tracks with the full Ormol pretty accurately. So this is a 3D case where the top row shows the state of the flame at different time during the simulation. So this is a fully chaotic system, turbulent flow. And here the bottom row shows the state of the flame at the same time, but using this reduced Ormol. So these are two different simulations, but after that we post-process the results. And all these green bullets here, the spheres here, actually show you the row selection. We are not showing the column selection, so the column selection here would mean at any given time we only solve the species mass fraction for certain species, not for all of it. And so all the details of this is in this recent paper that came out a couple of months ago. A lot more details here. So here we actually calculate the statistics comparison of the DNS. So what you want to look at here is the DNS, which are the circles, and the thick red lines. The blue lines are for a different mechanism. So we don't expect that to match with that. So Jiang is the name of the mechanism. So you see the red and black actually match pretty well. These are for different species. These are statistics of the turbulent flow rather than instantaneous profiles. So it gets a very accurate representation of this, and these are RMS values, a lot of these, so which are harder to match. And this is all done on parallel computing, so the algorithm is easily, you can easily extend this algorithm to parallel computation. And so this is a wiki scaling analysis for a fixed rank here. We fixed the rank, so because we didn't want the rank to contaminate the analysis, the scaling. And as we increase the number of processes, you see the wall clock time actually fixes. So here the size of the problem increases as you increase the number of processes, and wiki scaling is that the CPU time remains the same. So as we increase the number of processes, we increase the size of the problem. All right, let me just summarize here where we are. And what I would like to learn more about is that so what we take a dynamical system in this form and we matricize or tensorize this. The key question is that how? And I still do not have a good answer because this is very problem dependent, how you matricize or tensorize. And a related question, so these are not two dependent questions. Actually, they are tightly related when you think about it more. Is that, okay, let's say we tensorize this, then what kind of low-rank tensor approximation we pick? I didn't talk about Tucker just for the sake of time, but we extended this to Tucker as well. So what kind of these? I mean, this is just three. I mean, we have, there are, the number of choices is enormous. And then which tensor network is appropriate for that problem? So I think these are interesting questions that we are still thinking about. But what we are doing, actually, we are extending this interpolation algorithm to more complex tensor network structures, allowing to solving generic PDEs on a given tensor network. I think we have the building blocks by tensor train and Tucker tensor. I don't know we can do every one of them, but at least we have a way to figure out cross approximations for more complex networks, and that's what we are working on. So, but no matter what you do here, essentially, it ends up, this whole algorithm ends up being solving the existing PDEs at at certain points. And these points evolve with time, depending how you tensorize this and what tensor low-rank approximation you pick. And these points evolve with time. That's extremely important. You don't want to have fixed points because the solution evolves, and so you have to adapt this. But the tensor part of this actually is hidden from the PDE. So that's why it's relatively easy to implement this compared to the existing one, which was based on dynamical low-rank approximation. You can solve the PDE at these points because you have PDE requires, because of differentiation operator, you need to know the neighbor points, but you already have this entire solution in the low rank form, so you can evaluate the neighbor points from the low rank. So in that sense, you just need to write a wrapper around your existing solvers and just call it. The number of points here is really the size of reduction. So if you calculate that, this is the total number of points. This is the number of these points compared to the full point is the compression, the inverse of that is the compression ratio. So in fact, reduced order modeling here translates to solving the PD at fewer points. And that's so it's a very interesting way of thinking about low rank approximation and reduced order modeling, because it directly targets certain degrees of freedom in the existing PD. Anyways, I think it's fascinating, the quantum inspired reduced order modeling. I didn't talk about the data compression side of things. I think that's also fascinating and just purely data driven and building surrogate models. And essentially with the interpolation, this is really related to active learning, machine learning. And also on the CFD side and high fidelity simulation, most of the stuff I presented was on this side. I mean, all of it was on this side. But I think this has a lot of potential to go from essentially the way we do this scientific computing, at least in fluid dynamics, is scale resolving. So we add enough degrees of freedom to capture the smallest scales that are relevant to the physics of the problem. By doing the scale resolving, we add way too many degrees of freedom that are necessary, essentially, if you think about it. And so this kind of reduced order modeling ends up giving you a structure resolving problem where that degrees of freedom, that grid points and resolution comes at very low cost, so you can actually increase the resolution, not worrying too much about the computational cost. So I really think this is my the big picture takeaway from these algorithms. I'll just have some of the selected papers in the past 2 years, 3 years, which I cover. I covered this paper. So if you, the first paper we introduced this for PDEs is this paper, and then we extend. So this also I covered this paper, which is the extension to combustion, and also JP5, where you can find the details of this for Tucker tensor and tensor train manifold. And with that, I'll just take any questions you may have.
Yeah, thank you. That was an amazing talk. I really like linear algebra. So it was really fun to see all of those matrices at the beginning of your slides. It's fun. Maybe we can get the discussion started. The questions are coming in on Discord. I mean, I can ask my own question. So, one of the, I guess I have two questions, but let me ask my first question. So what happens when your overall matrix, it's not easily approximated by a low rank matrix? And one of the things that I worked on in the past is these classes of hierarchical matrices, right? Where different pieces of your matrix, there are different subblocks that can be approximated by low rank approximations, but not the entire matrix. So how does kind of your technology extend to these classes of hierarchical matrices?
So it doesn't. So this is exactly goes back to how you matricize and which kind of low rank approximation. So because if the matrix is not low rank or tensor is not low rank, this algorithm doesn't offer anything. So in fact, I see that as a separate problem. So you have to first come up with a way to extract these low rank structures. So that's I think of that as a separate question than interpolation. So um, that's exactly this challenge that we are dealing with. Exactly. So because this is not a recipe, you have to come up with a tensorization and tensor low rank approximation where you can do a lot of compression. So what we do it offline, typically in a in not a rigorous way. And I'm pretty sure the tensor architectures we come up with are suboptimal because of that, because we are not following a rigorous algorithm here.
Mm.
It's just more intuition, how, you have to know your problem and just stop playing with it. And there are some algorithms that are coming out that allows you to, for a given problem, find which tensor is better and which hierarchical
Mhm.
Tucker tensor, for example, is better.
Mhm.
So essentially, what is that good tree or tensor network architecture for a given problem?
Mhm.
That's a separate problem. Once you have that, then you can start using this algorithm. So interpolation on its own does not at all address that question that you pose. It's an extremely important question, but we see this as a separate thing. So if you don't, essentially, if you don't have low rank structure, you shouldn't use this kind of low rank approximation to begin with, no matter.
Mhm.
So just take it to a form that is low rank and then.
Mhm. Yeah, usually some of those matrices, they're not, the overall matrix is not low rank, but there are
Okay,
different
that's right.
subblocks that are there. So there's like equivalent hierarchical interpolative
That's
factorization. There are equivalent kind of
exactly. No,
things.
so we do tensor quantics actually for a lot of problems that are not low rank in the matrix form. When you do tensor quantics by tensorizing it to a 2 to the power of d, or if you do
Hmm.
interleaving, you get like 4 to the power of d, 8 to the power of d.
Mm.
You get a lot more low rank. So quantization, but it's not just quantization exactly like you said. So sometimes a subblock is much more low rank, and so you have to do this low rank approximation and a domain decomposition basis, all of that. So, but that's like I said, um, uh, to me that goes to the how and what here.
Yeah. Okay. Fair. Thank you. Yeah, we have some questions on Discord. I can read them out to you. This is a question from Ashley. I noticed the really cool reactions displayed. How can you apply these concepts to quantum chemistry?
So um, that's a I don't know a lot about quantum chemistry, but I think again I would go back to I would look at the problem and see if we can come up with a low rank structure. So again, you can separate this thing uh, in two steps, and this is how we always think about these problems. And this is going back to the previous question. So quantum chemistry, I would come up with a tensor network that you can compress that problem in that particular tensor network. And then we will develop an interpolation algorithm for that specific tensor network. And then we can solve it. So what it allows you to do here in terms of chemistry, the chemistry part is usually quite involved if you look at the functional relationship in the chemistry, because it involves empirical interpolation, empirical polynomial fits, thermodynamic tables, at least in turbulent combustion, where you have high temperature and temperature varies, the reaction rates are temperature dependent. So what interpolation offers to you, it allows you to handle that kind of nonlinearity essentially with ease. So that's how I see it. But I'm not an expert in. Unfortunately, I don't have any more meaningful thing to say in terms of quantum chemistry. But again, for any new problem, that's how we approach it.
Mm. Thank you. Another question from Mohammad Reza. So when earlier the concept of low rank approximation was being discussed, it was clearly reminiscent of PCA, wherein you align the axis containing the highest degree of variance in your data, you achieve more and more representation. Would you say that this is purely due to the applicability of SVD in PCA, or one can envisage a quasi-variance in work behind the scenes for any matrix in this context?
So PCA would be POD exactly, if I wanna put it in the context of my presentation. POD in fluid dynamics is exactly nothing but PCA. It's PCA. So I mean, all of these at some point, even a tensor formulation relies on an SVD. It's either HOSVD or TTSVD, but all of them rely on SVD. But that's exactly the case. So what we do here, essentially, the good way to think about this is using. So you need to have the low rank structure in that SVD form in anywhere you use SVD. Otherwise, you don't get that much compression anytime you perform the SVD. The good way to think about this is that anytime you take SVD, we are replacing that with COR, right? So that's really which you get a slightly, the cost you pay is that the accuracy is reduced compared to SVD, so it's not as accurate as SVD, but you need access to fewer entries. So this is the connection of PCA and which PCA is based on SVD and COR. But again, maybe the question is broader than what I discussed. Um, yes, this looks at SVD, but it's an SVD on the fly essentially. So you don't do any of these because when we do PCA, it's usually in a data-driven fashion. You collect data. So this is instantaneous SVD maybe, or instantaneous COR, as
Mm,
opposed to an offline SVD.
yeah. Okay, thank you. Another question from Hussein Shiri. As the algorithm contained advanced mathematics, how can we start in designing such algorithms? What are the recommended prerequisites and approaches?
Excellent question. Let me just, I can. So I think I would start by, let me just go back. So mathematics here is essentially linear algebra. And if you want to understand the interpolation side of things, I highly recommend this paper, 2010, which is an excellent paper, science paper. This would be a good start. Then extension of that to COR probably our paper actually we explain things in details. The 2023 paper, so I recommend that. There's also this paper by Sorensen to 2016. So I would recommend understanding this at the matrix level because it's just much easier. And then once the matrix level is understood, I think tensor becomes much easier. But in terms of extending this to different tensor, um, each tree, for example, if you do hierarchical tree, will have its own set of interpolation points. And you have, essentially, if you combine TT and Tucker, you have the building blocks to do it for more complex trees.
Thank you. Maybe I can ask one question from my end. So, we discussed all like this quantum inspired approaches and like developing these methodologies that you described in this talk. I know, can we kind of go back to quantum algorithms? Like what I'm saying is like, can we take some of these reduced order models kind of and go back and try to like develop quantum equivalent quantum algorithms for these approaches that can be implementable in a quantum computer?
Oh, okay. So you're talking about, so not just a quantum algorithm doing this on quantum hardware.
Yes.
Okay, that's uh, we have Juan Jose in our department who is an expert in quantum hardware. I cannot speak to that unfortunately, but that's something I would love to explore more. Exactly. So, but we are not at that stage yet. But we had several conversations with him to do the quantum hardware. But I'm not an expert in quantum hardware, so unfortunately I cannot answer that question.
No, thank you. I think it's kind of just an interesting line of work in itself. Um,
Absolutely. Yeah, that's an interesting question, but it needs a collaboration with people who know quantum hardware and see how we can actually exploit these algorithms. So I think what these algorithms allow you to do in terms of algorithmic is that allows you to solve essentially generic PDEs
mhm.
rather than assuming any sort of structure like Hamiltonian linearity, stuff like that. So it would be very nice to see how this can be done in terms of quantum hardware aspect of it.
Uh, Yeah, sounds good. Uh, Thank you. I see people typing on Discord, so I'm going to give a few minutes, see if we get more questions. Yeah, maybe I can ask you a broad question. Through the summer program, we have a lot of our participants participating in projects with our industry partners. What kind of advice would you give to them? And one of the projects I think from BQP is actually on doing based on tensor networks. And for people doing that, what kind of advice would you give to them?
That's a good
How
question.
to approach these research questions?
I think one thing that has worked for me if I approach a new problem um, is that I ask them if they already solved the problem. Usually, a lot of these industrial applications, they already have solved the problem. They just want to accelerate it, essentially. That's been most of my interaction with the industry or practitioners, I call them. They might be in academia, but they're solving a PD. So what I do, the first thing I do before actually doing any of this implementation, which requires investment in terms of time, I would
Mhm.
just take the data from them and work on data to find out which architecture is how we can compress that data. That's usually the first step I do when I encounter a new problem.
Mm.
And then I'll do all of that work, which is much easier to do just working with the data and essentially manipulating data and exactly what, like you said, finding out which part of it you can do low rank approximation, what kind of low rank approximation gives you the most compression, all of that. And then essentially come up with a tensor network. And then once we have a good tensor network, then the rest of the methodology, like I said, then I would approach it in terms of now, if the goal is acceleration, then you can actually now develop interpolation algorithms to solve that PDE. This has worked for me if you ask for advice in terms of minimizing the waste in terms of your time and your collaborators' time, and to get to a good solution without actually committing to do a full-fledged implementation to figure out whether this algorithm works or not.
Mm.
So the key with these algorithms is that they're kind of also fragile. Like in my experience, the whole tensor low-rank approximation, because if you don't have low-rank structures, then none of these methods work.
Yeah.
But if you do have low rank structure, then you can essentially, it's hard to compete with it with existing methods. So you have then then the key question is that to formulate the problem in a way that you see the low rank structures. Going back to your first question, uh, so then I would like to spend all of my time if I see a new problem to find the low rank structures first. Because I'm not worried too much about solving that anymore. In fact, these past few years have taught us that now with these new techniques, actually solving this as if you find the low rank structures, right? Then solving this is easier. So that's the advice I would give. I mean, different people come to us for different purposes. Most of the people come talk to me is because they want to accelerate computations. This is on the PD side of things. But there is side of things that are purely data driven. I'm working on regression, essentially supervised learning. If you don't have a ton of data, labeled data, that's another application which is not PD related. Depends on the application, but most of the people come to me for computational cost issues. So like I said, it's unfortunately right now the way we do it is based on intuition. It's a tedious investigation of the data. We do visualization, we look at the data. Ideally, you want to replace this human part of this with an automated approach, but we don't know how to do it yet.
Yeah. Yeah, that's a very valid point. Kind of having some kind of repository there or like a code that can just kind of look at your data and able to identify like different
Absolutely.
low-lang blocks would be amazing.
That's right. Exactly.
Yeah, thank you. We have two more questions on Discord. Maybe we can just take them. I know we are running a little bit over time. Okay, I'm just gonna read them out to you. This is a question from Alma. So the DEIM-CUR for Tensor, is it equivalent to the compressed row storage for sparse matrices? There any equivalence
No.
there? No.
No, I mean, so the compressed raw storage, it's a lossless compression. So you don't lose any information. Here, this is actually low rank approximation. So you lose, so there is an error here.
Yeah.
This matrix is also a full matrix. None of these matrices we talk about are sparse matrices. So these are all full matrices. So this is the state of the system, not the discrete. So there is a lot of low rank approximation for discretization matrices, right? So if you have a discrete as your differential operator, those matrices usually are sparse because we use either finite difference, finite element. All of these techniques lead to sparse matrices, and then you can do compressed storage of those CSR. That's lossless. Or you can do even low rank approximation. Here we're talking about doing a low rank approximation of the solution of the PDE, which is usually not sparse. And these are no matter if you tensorize these matrices, these are full matrices.
Thank you. Yeah. One last question. It's a very broad question for you. This is from Cheryl. It looks like quantum computing is causing a new expansion of study in new ways to solve differential equations. Is this a correct impression? And a follow-up to that, are there other kinds of math or computing algorithms for problem solving that are also being studied in new ways due to quantum computing?
So,
And
okay, let me answer this. I think what is fascinating in terms of applied mathematics, absolutely fascinating, is that you can approximate high dimensional functions with linear cost or polynomial cost in terms of dimensionality.
Mhm.
So if you have a d-dimensional function, uh, you have to pick the right tensor network. But if you do, then like this DMRG, you can essentially. So this is what is fascinating beyond quantum, because quantum you work with high dimensional problem. But Schrodinger equation is a high dimensional PDE. So algorithms that are developed to solve Schrodinger equation has much broader applicability than just the Schrodinger equation. And the reason is that approximating a high dimensional function with the cost of polynomial or linear cost in terms of dimension is breaking the curse of dimensionality, essentially, if we can do that. And what quantum, and then now the extension of these algorithms in applied math allows you to solve a whole bunch of other problems. So what I see as the key contribution of this quantum inspired algorithm is being able to approximate high dimensional functions with much with the computational cost, like I said, linearly dependent on dimension or polynomially. And that's, I think, that if I mean, I guess different people have different perspectives about this. Maybe this is a very narrow angle I'm looking at this. But I think if I were to pick one quality of these algorithms, is that, I mean, we know neural networks, for example, do not also suffer from the case of dimensionality in approximating the high dimensional functions. But with neural networks also comes a lot of challenges, especially if you want to use them in scientific computing, because you essentially turn everything to this nonlinear, non-convex optimization problem, which are difficult to solve, very expensive to solve. Sometimes it makes actually the problem more expensive than solving the original problem, sometimes many orders of magnitude. I know that's an active area of research, so this is not done. I mean, people are working on that. So, but the snapshot we are looking at right now. With Tensor, if you can approximate a high dimensional function using this form, you usually have pretty amazing optimization algorithms to do any kind of task you want to do. So there are these amazing Riemannian optimization. So essentially, anytime you take an SVD, SVD is actually solving an optimization problem for you. It's finding the best low-rank approximation. And SVD, we have pretty fast algorithms for SVD or COR. So that's where I see the main contribution of these quantum-inspired algorithms. That's why I think it has much broader applicability than quantum chemistry or quantum many-body problems.
Thank you. Yeah, that was a great answer. And I think if I can add on to that, I think for me what's exciting is it's putting linear algebra back on the map again. It's a field that's been around for a long time, but now now people are thinking about like how can we use linear algebra to develop better quantum algorithms or into quantum inspired algorithms, like bringing up like more clever ways of using known existing concepts of it and combining them in new ways.
Absolutely. In fact, so this was actually a few questions ago. So the main math side of things is linear algebra. Absolutely, you're right. So if you want to know the basics of this, is all linear algebra, and that's helped us quite a bit, because all of this work we do is actually it's informed by and benefited from linear algebra.
Yeah. Thank you. Last question's kind of a third part to Cheryl's question. So all of these new developments that are happening, is this only due to the need for data input to be in a matrix format for quantum computing?
Not matrix, it could be tensor. I mean, I presented this in matrix. Um, so we do these developments completely um, being actually kind of ignorant about quantum hardware part of it. We are interested in the algorithmic part of this, which is essentially the applied math side of quantum algorithms. So yeah, so it's matrix or tensor, but we are not looking at the hardware side of things. We are just looking at the algorithmic side of things.
Yeah. Awesome. Thank you so much. This was an amazing talk. I learned a lot, and it was actually really fun for me to see all this amazing work that you presented. Thank you so much. And everyone's like, I'm sure it benefited a lot of the participants. And thank you so
Thank you so
much
much for
once
your
again.
kind invitation. I appreciate it. Enjoyed it.
Yeah, thank you. All right. And yeah, that's all we have for today. And I'll see everyone on Monday for some interesting talks on quantum chemistry. Thank you, everyone.